In classical mechanics, under the topic variational principle, you have seen the Hamilton's variational principle in previous lecture. Now today we are going to discuss its illustration. Actually, the first illustrative example we will take the problem of linear harmonic oscillator. In fact, the problem of a linear harmonic oscillator is a common problem of classical mechanics, and this problem is solved by various methods, various approaches. Today our aim is to find the equation of motion of this one-dimensional linear harmonic oscillator by using the concept of Hamilton's variational principle. So let us see. As you know, a one-dimensional linear harmonic oscillator is visualized just as a spring mass system. This is just an example of a linear harmonic oscillator, and you can see this figure. I have considered a massless a spring, say of a spring constant K, whose one end is rigidly fixed to a wall, and a block of mass m is attached to its another end. In fact, when the spring is unstressed, then actually this mass is in equilibrium, because in this condition two forces will act on this mass. This is mg, that is the force of gravity, and the normal force exerted by the surface on which this mass is placed. Under these two forces, actually the mass is in equilibrium, that is net force is zero, because a spring is unstressed, so no spring force acts on the mass. But when this mass is slightly displaced from its equilibrium position and released, then what happens? You know, the spring force is developed, and due to that spring force, this mass actually oscillates about its equilibrium position. And if you consider that from its equilibrium position the mass is displaced by x, then what will be the kinetic energy and the potential energy of this spring mass system when the mass is at its displaced position? You can easily say. So you can see that consider a spring mass system as an example of a linear harmonic oscillator. In fact, this is one-dimensional linear harmonic oscillator, and from its equilibrium position this mass is displaced by x, as I have told you. That let us consider that x is displacement of the mass from equilibrium position at a time t equal to t. As you know, this mass oscillates under the spring force, which is actually a conservative force, and the position of this mass is always on this horizontal surface, so position is in fact constant. And you know, when the position of a system is constant, then the constant is known as holonomic. And since the spring force is a conservative force, so you can say that this linear harmonic oscillator or this spring mass system is a holonomic conservative system. And you know, the Hamilton's variational principle is applicable in case of holonomic conservative system. So we can apply the concept of Hamilton's variational principle to solve this problem. Actually, we will solve this problem by two methods. So say this is our first method. This is first method, let us say. To apply the Hamilton's variational principle, we need to find the Lagrangian of this system, because you know, according to Hamilton's variational principle, the delta variation of the time integral of Lagrangian L is equal to 0. So first of all, we should find what will be the Lagrangian of this system. And to know the Lagrangian, you have to calculate the kinetic energy and the potential energy of this system. As you know, this system has two parts. One part is a spring and another is mass. Since a spring is massless, so it will have no kinetic energy. So kinetic energy will be only in this mass, and that kinetic energy will be actually the total kinetic energy of this system. So when you say kinetic energy of the system, what does it mean? It means kinetic energy of the mass, because due to zero mass, a spring has no kinetic energy. So first of all, we will find the kinetic energy of this system. So kinetic energy of this system. Actually, kinetic energy will be sum of kinetic energy of the mass and the spring, but a spring has zero kinetic energy. So this is simply equal to kinetic energy of the mass, and this will be half m x dot square, because you know x dot means what? This x dot is dx by dt. This is actually velocity of the mass at any time t. So this is simply half mv square. And as the motion of the block takes place on the horizontal surface, so its potential energy may be taken as constant, because there is no change in the height of the object, and so gravitational energy, potential energy will be constant, and for convenience we take it 0. So you can take the gravitational potential energy of the mass as 0. So only the spring will have potential energy, and so a spring's potential energy will be called total potential energy of this system. So you can say potential energy of the system, and you know, if K is the spring constant, then potential energy V of this system will be what? You know, it is half kx square, and kinetic energy is denoted by the symbol T. So T is equal to half mx dot square, this is T, and V is equal to half kx square. Now you can find the Lagrangian of this system. So Lagrangian of the system. What will be the Lagrangian of this system? You can say L, you know, is equal to T minus V, and so this will be half mx dot square minus half kx square. This is Lagrangian of this system. Now actually we will apply the Hamilton's variational principle. So you know, by Hamilton's principle, or you may say Hamilton's variational principle. You know, this principle states that the delta variation of the time integral of Lagrangian is equal to 0. Now let us substitute the value of this Lagrangian L which we have obtained here. So you can say this is delta of T1 to integral T1 to T2, and this is half mx dot square minus half kx square dt, and this equal to 0. So now as you know, this delta may be operated on this. In the proof of Hamilton's variational principle you have seen this thing. So we can write this equation in this way. This is integral from t1 to t2 delta operated on half mx dot square minus half kx square dt, and this equal to 0. Now see here, when you will operate this operator delta on these two terms, what will be the result? You can easily see this delta will be, when operated on this, you can see this will be half m, this is a constant factor, times, now delta will be operated on x dot square. So this will be in fact 2x dot delta x dot, and minus, when this delta will be operated on half kx square, here also half k is constant, and when delta will be operated on x square, the result will be what? This will be 2x times delta x dt, and this equal to 0. This is t1 to t2. Now you can see this equation may be written as integral t1 to t2. See here, this half, this 2 and this 2 will cancel. Here also this 2 and this 2 will cancel. So this is simply mx dot delta, this is delta not d, mx dot delta x dot minus kx delta x dt equal to 0. But you know, when we were discussing the Hamilton's variational principle, then we have explained that this delta x dot, actually this is equal to d dt delta x. You have already seen while we have discussed the Hamilton's variational principle, this result. So the first term inside this square bracket can be now written by the use of this relation. You can see what will be this term. So we will write integral t1 to t2 mx dot times delta x dot, but delta x dot will be now written as d dt delta x, d dt delta x, and dt, and minus integral t1 to t2 kx delta x dt, and this equal to 0. Now we will integrate this first term by using the rule of different integration by parts. So let us see here. We will take that this x dot is the first function, and this d dt delta x is the second function. So considering x dot as first function and d dt delta x as second function, we will integrate this first term. So after using the rules of integration by parts, you can see what will be this result. So therefore, we in integration by parts we write first function. So first function will be x dot, m is constant, so you can write mx dot, and integral of the second function, you can see integral of d dt delta x with respect to t will be simply equal to delta x, because this will be differential of delta x, and integral of differential of delta x will be simply delta x. So the first term will be what? This will be mx dot, this is first function, and integral of second function is delta x, and limits are t1 and t2. Now there will be minus integral of t1 to t2. Then in the formula of integration by parts, you know there is differential of first function. So first function is x dot, so we will differentiate it with respect to t. So this is d dt x dot, and times integral of second function, and you have seen that integral of second function is this delta x and dt. Actually this result has been written at the place of this first term by using the rule of integration by parts. And now write exactly same the second term here, and you can see this will be minus integral from t1 to t2 kx times delta x dt, and this equal to 0. Now you can see in delta variation, you know this delta x is equal to 0 at the end points, and at the end points time is t1 and t2. So you can say this delta x is equal to 0 at t equal to t1 and also at t equal to t2. So corresponding to these limits, this delta x will be 0, and so this first term will actually vanish. So first term is 0. In above equation, the first term is 0. And that is, you can say that this mx dot delta x at t1 and t2, this equal to 0. And so our result is what? You can see now this result will be actually equal to now minus integral t1 to t2 m d dt x dot delta x dt minus integral t1 to t2 kx delta x dt, this equal to 0. And now let us simplify this LHS of this equation. You can see delta x dt may be just written as a common factor, and integral has also the same limit, and both terms are negative. So in fact, when we will take the minus 1 as a common factor, then both terms will become positive. So you can write this is integral t1 to t2 now d dt x dot. When you will differentiate this x dot with respect to t, that will be simply mx, that will be simply x double dot. So this is mx double dot and plus kx plus kx and delta x dt, and this equal to 0. This equal to 0. Now you can see this delta x is completely arbitrary, because along the path we can take this delta variation of x at anywhere. So delta x is arbitrary. This is arbitrary. So if this delta x is arbitrary, then definitely this equation will be satisfied or will be valid only when this term mx double dot plus kx is equal to 0. So due to the arbitrariness of delta x, we can say that mx double dot plus kx is equal to 0, or you can take this m as a common factor. This will be x double dot plus k over m x equal to 0. But you know this m is not 0, so definitely x double dot plus k over m times x, this is equal to 0. Or you may write in this manner, this is d2x by dt square plus k over m x equal to 0. And you can see this is actually the equation of motion of this linear harmonic oscillator. You can see this equation is nothing. This is simply the equation of motion of SHM. This is equation of SHM. So equation of motion of the oscillator, and this represents simple harmonic motion. So you can say that this linear harmonic oscillator actually executes simple harmonic motion about the equilibrium position. Now comparing this equation of motion of this linear harmonic oscillator to the standard equation of SHM, you can find what will be the frequency of oscillation or the time period of oscillation of this oscillator. You can easily find. You know, a standard equation of SHM is what? A standard equation of SHM. This is in fact d2x dt square plus omega square x equal to 0. And here omega is actually the cyclic frequency of SHM. So when you will compare this equation of motion of the linear harmonic oscillator with equation of SHM, you can easily recognize that omega square is equal to k over m. So comparing these two results, you can say omega will be equal to a square root of k by m. And you know, if nu is the regular frequency, then omega will be written 2 pi nu, and that will be equal to root under k over m. And therefore you can say the frequency of oscillation of this oscillator is equal to 1 over 2 pi root over k over m. So this is actually the frequency of oscillation of this oscillator. So this was actually the first method to solve the problem of linear harmonic oscillator. Now in the second method, you will see we will apply actually the technique of calculus of variation, and again we will solve this problem. So let us see what is this second method to solve the problem of a one-dimensional linear harmonic oscillator. Actually, again, we will start with the Hamilton's variational principle for this linear harmonic oscillator, and then we will follow the technique of the calculus of variation. So you have seen by Hamilton's principle, you know that delta variation of the integral from t1 to t2 L dt is equal to 0. And you have just calculated what is this Lagrangian for this linear harmonic oscillator. You have seen this Lagrangian for linear harmonic oscillator is simply half mx dot square minus half kx square. Actually, this is kinetic energy and this is potential energy V of this system. And so L T minus V is Lagrangian, and this equal to 0. Now, according to Hamilton's principle, if delta variation of this integral is 0, then definitely this integral will be extremum. So you can say that this result implies that integral t1 to t2 half mx dot square, this is mx dot square minus half kx square dt, this will be extremum according to the Hamilton's variational principle, you know. Now you can see this, if we consider that this is a functional f, then that functional is actually a function of x dot and t. So you can write this equation as integral from t1 to t2 f of x dot and t dt, and this equal to extremum. In fact, what is this f? You can easily see. Actually, this underlined expression has been assumed to be f. So you can say where this f is equal to, in fact, half mx dot square minus half kx square. Or you may say that the Lagrangian L is here the functional. And you know that this equation holds, that is this integral is extremum only when Euler-Lagrange equation is satisfied. So definitely we can say that as this condition is holding in accordance with the Hamilton's principle, so we can use the Euler-Lagrange equation in this condition, because Euler-Lagrange equation is the necessary condition for this integral to be extremum. So you can say if equation, I have assumed equation number or not. Let us say this is in fact equation 1. Let us say. So if equation 1 is correct, or if this equation holds, you can say it must satisfy Euler Euler-Lagrange equation. And what is Euler-Lagrange equation? You have studied this Euler-Lagrange equation in very detail in the previous lectures. So you can say this is d dt del f by del x dot, because you can see at the place of x here is in fact t, and at the place of y there is x. So this will be d dt del f by del x dot and minus del f by del x, and this equal to 0. Or in fact, as you have seen that this f is nothing, this is simply the Lagrangian L. So you can also write L at the place of this f. You can write it. Now, let us say this is equation number 2. Now, first of all, we will find the partial derivatives del f by del x dot and del f by del x. As we have defined this f here, you can say this is the value of f. So from the value of f, now first of all find these two partial derivatives. Now del f by del x dot, what will be this? This is del x dot, and f is what? F is simply Lagrangian, and this is 1 over 2 mx dot square minus half kx square. You can see when this operator will be operated on the first term, this will be half m because it is constant, and x dot square will be differentiated with respect to x dot, and that will be 2x dot. And the derivative of this second term will be 0 because it is not a function of x dot. So in fact this is simply mx dot. This is mx dot. Now again we will find del f by del x. What is del f by del x? You can see this is del x, and again f is half mx dot square minus half kx square. And you can see when you will operate this operator del x on the first term, the derivative will be 0 because in first term there is the first term is not a function of x. But what will be the DC of second term? You can see this is minus half k times 2x. So this 2 and 2 will cancel, and so del f by del x is minus kx. Now you have obtained the value of del f by del x dot here, which is mx dot, and del f by del x, which is minus kx, you have obtained. Now let us substitute these two values in equation 2. So see this equation and substitute these two values. So substituting these in 2, you can see this is in fact d dt del f by del x dot, but we have obtained the value of del f by del x dot, and that is mx dot, and there is minus sign here, and del f by del x, that is equal to minus kx, and that equal to 0. Now m is constant, so this operator d dt will be operated on x dot, and so it will be mx double dot, and this minus minus will be plus, this is kx equal to 0. So again, when you will take this m as a common factor, this will be x double dot k over m times x equal to 0. As m is not 0, so you can say this is x double dot plus k over m times x equal to 0. So you can see this is the equation of motion of your linear harmonic oscillator, that is one-dimensional linear harmonic oscillator. So you have seen by these two methods how simply we can solve the problem of the linear harmonic oscillator by using the variational principle. So this is actually a very strong and powerful method to solve such problems.